Phase 0, Digital Literacy, Module M0.1. Peek inside the box. You've probably heard the terms CPU, RAM, and storage thrown around a million times.
Oh, yeah, absolutely. Constantly.
Right, but instead of just defining what these parts are, our mission today is to figure out exactly how these three fundamental hardware components collaborate to prevent your machine from, constantly tripping over its own feet.
Because a computer's architecture is entirely built around managing bottlenecks. So queuing up slide 1 here, at the center of it all is the central processing unit.
The CPU.
Right, the CPU. It's the brain doing the actual thinking by running step-by-step instructions. But what's fascinating is the incomprehensible scale. The documentation clocks a typical modern CPU at 3.5 gigahertz.
Right, which means 3.5 billion execution steps happening every single second.
Yeah, it's staggering.
The source material uses that classic analogy. The CPU is a chef frantically chopping ingredients. But wait, if you have a processor slicing through billions of operations a second, there's a massive physical constraint.
Oh, for sure.
Like, if the CPU is the chef working at billions of steps a second, where are they keeping all their ingredients so they don't slow down? I mean, they can't be walking across the kitchen between every single chalk.
No, exactly, which transitions us nicely to slide 2. That physical constraint is exactly why random access memory, or RAM, has to exist.
And we usually see, what, like 8 to 32 gigabytes in a standard setup?
Yeah, exactly. It's the temporary workspace. If you think about it, it's like a desk where you keep all your open papers.
So more RAM just means a bigger desk holding more open apps at once.
Precisely. But it's really about the physics of retrieval. RAM is incredibly fast, allowing the CPU to read it instantly so it never has to wait.
But the trade-off for that speed is volatility.
Yeah.
Right? The moment the power drops, that workspace is
wiped completely clean.
Yes. But why design a system like that? Why make a workspace where a simple power outage destroys everything?
Well, to achieve the nanosecond response times the CPU demands, RAM relies on capacitors that constantly need electrical refreshing. The moment that power goes off, the charge dissipates and the data instantly vanishes. It prioritizes sheer speed over permanence.
Okay, so because RAM is volatile, we obviously need long-term storage, which brings us to slide 3.
Right, detailing storage. We're talking solid-state drives and hard drives.
Ranging anywhere from 256 gigabytes up to 2 terabytes now.
At least, yeah. And unlike RAM, storage is permanent. It survives a shutdown and keeps your files safe.
But let's push back on the system design for a second. If storage holds up to 2 terabytes of permanent data and is fast, why do we even need RAM?
Well,
Why doesn't the CPU just read directly from the massive storage?
This raises an important point about how we perceive speed. What's fast to us is an absolute crawl for a 3.5 gigahertz CPU. Storage serves as the filing cabinet. It's massive, but it's much slower than RAM. Retrieving data takes milliseconds.
And to a CPU operating in nanoseconds, a millisecond is an eternity.
A massive eternity. If your processor had to fetch every single one of those billions of instructions directly from the permanent storage, the bottleneck would render the CPU speed completely pointless. Your computer would just constantly freeze.
Okay, so transitioning to our final slide, slide 4, let's walk through the actual flow. When you double-click an app, what exactly happens?
Right. Step 1, the app is sitting completely dormant in the permanent storage drive.
Safe, but totally inaccessible to the fast-moving processor.
Exactly. Then step 2, the moment you click, the system copies that program from the slow storage filing cabinet and loads it directly into the lightning-fast RAM.
So bringing the analogy back, we move the ingredients from the deep storage pantry right onto the active counter space.
Yes. And finally, step 3. The CPU pulls the data directly from that RAM. It runs the application, unhindered by the slow retrieval times of permanent storage.
So the pantry to the counter to the chef.
Precisely. And connecting this to the source material leaves us with a really compelling thought.
Oh, what's that?
Given that a 3.5 gigahertz CPU relies entirely on the temporary countertop of RAM to feed it billions of instructions a second, consider the sheer fragility of active computing.
Right.
A single fraction of a second power blink wipes that counter completely clean before anything can be saved back to the permanent filing cabinet.
Wow.
We are analyzing why computers fundamentally only understand on and off, and, well, how that crude binary foundation literally becomes everything digital.
Yeah, it's the absolute bedrock of the technology.
Okay, let's unpack this, because it's basically like building a highly complex universe using only one type of microscopic brick.
That is a really great analogy, actually. And I want to establish right away that understanding this specific slide deck is absolutely essential for your technical literacy.
So providing a clear transition here to the second slide, we introduced the bit.
Yes.
The smallest unit of data possible. It's just a single switch, and it's permanently restricted to just two states, 0 or 1.
Right. You can compare it directly to a standard light switch. It's either up or down. But modern devices hold millions of them.
But wait, I have to push back on that to bridge to the next concept. If a computer just has millions of simple light switches, how does that crude binary mechanism actually translate to complex, usable information?
Well, if we advance to slide 3 here, we get to the byte.
Right.
This is where 8 of those individual bits are grouped into one single unit.
And the slide details the mathematical reality of that grouping, right?
Exactly. 8 switches gang together to create exactly 256 combinations, which happens to be just enough to represent one letter or symbol.
Oh, wow. So everyday terms that you hear, like kilobytes, megabytes, and gigabytes, those are simply massive collections of these bytes.
They absolutely are.
So if a bit is a single toggle, a byte is the first complete character the machine can actually read.
That is perfectly stated, which progresses us sequentially to slide 4.
Okay, binary counting, or base 2. Here's where it gets really interesting.
It definitely takes a conceptual leap here.
Yeah, because each switch acts as a place value in a sequence, right? Like 1, 2, 4, 8, 16.
Let me walk you through the specific equation on the slide to make that a bit more concrete.
Please do.
So, by turning on the 8, the 2, and the 1 places, the machine creates the pattern 1011.
Okay.
And that simply adds up to the standard number 11.
It's just a totally different way to do basic addition.
It really is.
So advancing to the final slide, slide 5, we finally see how these numeric patterns scale up to create your digital files.
Right, because literally everything is a pattern of bits.
Because letters map directly to numbers. The slide notes that the letter A equals 65, which is 01000001 in binary.
Exactly. And to synthesize the broader picture here, pixels and sound map to numbers identically.
So it's exactly the same system for everything.
Underneath your entire digital experience, yes, it is exactly the same on and off switches at work.
That is just incredible to think about. Millions of basic toggles layering mathematically to build your entire digital reality.
It really is an elegant architecture.
So what does this all mean for you?
Well, it leaves you with a final, rather provocative thought.
Let's hear it.
If every text, every image, and every sound is ultimately just a numerical pattern of bits, does that mean every undiscovered masterpiece is already waiting mathematically in some unexplored sequence of ones and zeros? So today, we are exploring a digital literacy deck called From Power to Program. The mission here is to trace that precise, physical, and logical journey, just to help you understand what running software actually looks like at the architectural level.
And it's such a profound transition, to unpack that journey. The deck starts us off on the first slide with a really familiar visual, the universal power button icon.
The literal spark of life for the machine.
Exactly. This is the boot phase. The moment voltage hits the motherboard, the firmware takes over.
So it's not just waking up then.
Right. It's running the power on self-test. It's verifying the physical memory architecture, the processor state, the peripheral buses, all of that hardware stuff. Only when that autonomic nervous system gets the all clear does it hand the reins over to the bootloader.
Wow. Okay, so if we look at it biologically, it's kind of like the moments before you open your eyes in the morning.
I like that analogy.
Like your brain is firing off rapid unconscious signals, basically checking to ensure your arms and legs work before your conscious mind even boots up to start your day.
That's an excellent way to frame it, because the conscious mind, in this system at least, is the operating system.
Which brings us to the next phase.
Yeah, the deck shifts here to the second slide. It shows an image of interlocking gears. This highlights the OS-like Windows or Mac OS as the master coordinator, sort of the always-on manager.
Okay, let's unpack this for a second. Is the OS basically the subconscious mind of the computer? Like, is it keeping the heart beating so the apps don't have to worry about the actual hardware?
It provides exactly that layer of abstraction, yes. The physical components, the CPU cache, the system RAM, the storage, they are finite. They have to be shared.
Right. There's only so much to go around.
Exactly. So the OS dictates memory paging, it schedules CPU time, and it isolates processes so they don't overwrite each other.
I mean, if every single application had to carry the code required to negotiate with your specific memory controller, software development would be impossible.
It would be a nightmare. The OS absorbs all that complexity. It's the boss in the background.
So with the OS managing all that traffic, how do we actually start an activity? Moving sequentially through the deck, we hit the third slide.
The rocket icon.
Right, representing the launching phase.
Yeah.
The text notes that on your local disk, an app is essentially inert data, a sleeping file.
Yeah, and it has to be copied into FastRAM to transform from a static file into a live process.
But wait, let me push back on that for a second. Why even move it?
What do you mean?
Well, modern NVMe solid-state drives are, they're incredibly fast.
Well,
Why can't the CPU just run the app straight from the storage disk?
it comes down to the brutal physics of latency, honestly.
Really? Even with modern SSDs?
Yeah, SSDs are fast for storage, but they are still orders of magnitude slower than the processor. RAM operates at nanosecond speeds, synchronized directly with the CPU's clock.
Oh, I see.
If a processor that's capable of billions of operations a second had to fetch its next instruction from a storage drive, it would spend 99% of its time just waiting around.
Forcing the data into the fast lane so the processor isn't starved.
Precisely. Copying it into RAM bridges that latency gap.
And that leads us to the final visual in the sequence, the fourth slide with the play button. This defines what running actually entails behind the screen.
Right. When a process is running, the CPU is just reading and executing the program's instructions in a strict order.
Over and over.
Yeah, it pulls an instruction from that active RAM, decodes what mathematical or logical operation is required, executes it, and writes the result back, doing this billions of times every single second.
Here's where it gets really interesting to me. Rather than just picturing, say, a hyperactive chef reading a recipe step by step.
Which is a fun image.
It is, but it's more accurate to envision an unyielding, microscopic factory assembly line, right? It fetches, decodes, and executes at lightning speed.
Right up until the user hits close.
And then what?
The moment you do hit close, the OS reclaims that memory space. The process leaves RAM entirely.
It really puts into perspective what happens between your finger tapping an icon and an app actually appearing. The hardware waking up, the OS managing the environment, the data migrating to high-speed RAM, and the CPU churning through billions of calculations.
Millions of steps in the blink of an eye just for you.
But it leaves you with a lingering thought. When you close an app, and those billions of lightning-fast calculations just stop, all that organized logic vanishes. Next time you click close, consider this. Does a digital process ever truly die, or does it just dissolve back into the silent potential of the hardware?
You drag a document into a folder and, it visually disappears into a neat little yellow icon. We all know the basics of files and folders.
Right, it's totally second nature.
Yeah, exactly. But the actual invisible engineering that prevents millions of scattered bytes from instantly corrupting into a chaotic, unsearchable mess, that is what we are unpacking in today's deep dive. We're looking at a digital literacy presentation on operating system architecture, specifically targeting how data is stored, named, and dynamically retrieved behind the scenes.
It really is a masterclass in abstraction. The visual interface tricks you into thinking about physical space, like real desks and folders. But to understand how an operating system structures data, we really have to look at the underlying logic.
So let's bypass the elementary definitions, right? We know files are basically just named containers holding bytes on a disk.
Yeah, and the extensions just tell the OS what application handles them.
Right. But physically, on the hard drive, there are no actual, folders. So how is the OS structuring this massive collection of byte containers so it doesn't just read the drive as one giant block of noise?
Well, it relies on a mathematical hierarchy, constructed entirely through text and memory pointers. Think of folders, or directories as they're technically called, not as physical boxes holding items, but as localized index lists.
Wait, so they aren't actually containers holding the files?
No, not at all. A directory is technically just a special type of file, and it contains a list of references or pointers to other files and directories.
Oh, wow. Okay, so it's less like putting a piece of paper in a manila envelope and more like, maintaining a localized phone book that only lists the contact numbers of the people standing in one specific room.
That's actually a much more accurate way to visualize it.
Right.
And because one directory's index can point to another directory's index, you generate that cascading nesting behavior.
Right, putting folders inside of folders.
Exactly. This creates an inverted tree structure. So when the OS is looking for something, it is not scanning millions of files simultaneously. It's reading node by node, branching down through these indexes.
Which, that brings up a massive navigation problem. If I'm the computer and the user hits search, I can't just blindly wander through millions of indexed nodes hoping to stumble over the right byte container.
Right, you'd be searching forever.
Exactly. The presentation highlights paths, basically folder names joined by slashes, as the solution. But mechanics-wise, how does the OS physically resolve a path?
Well, it depends entirely on the starting point of the query. And that is governed by absolute versus relative paths. An absolute path starts at the root directory, the absolute top of the tree.
Okay, so mapping the route from the very beginning.
Yes. The OS parses the text string, let's say /doc/cv.pdf, and methodically queries the root index for docs, then opens the docs index to find the pointer for cv.pdf.
But wait, if I'm already working deep inside a subdirectory, writing a script or something, querying from the root every single time I want to reference a neighboring file seems incredibly inefficient.
Oh, totally.
Like the OS can't possibly be running back to the top of the tree for every single local action, right?
It isn't. And that is exactly why relative paths exist. A relative path assumes your current working directory is the starting node. Instead of resolving from the root down, the OS just looks at the immediate localized index.
Ah, I see. It's the difference between using global GPS coordinates to find your own kitchen versus just knowing to walk down the hall.
That is a perfect analogy.
Yeah.
And the entity coordinating all of this traffic is the file system. The file system isn't just a static map. It's an active engine managing data structures called inodes.
Right. The presentation mentioned inodes, they store the disk block locations, right?
Exactly. They store the physical locations of every object. The file system translates those human-readable /text paths into the physical sectors on your hard drive in milliseconds.
So, synthesizing all of this, our entire digital environment is essentially a massive localized indexing tree. We create these byte containers we call files, we nest them into index lists we call directories, and the file system dynamically translates our visual clicks into precise /text paths.
Yep. The sheer complexity is completely hidden beneath a friendly interface.
Which makes you wonder about the future of that interface. I mean, we're still relying on rigid hierarchical folders and strict path addresses, a paradigm designed decades ago.
Yeah, it's pretty old technology conceptually.
Imagine when operating systems fully integrate AI at the kernel level, shifting from this rigid tree structure to like an associative memory model. You wouldn't need folders or paths at all. The system would retrieve data based purely on context and meaning rather than where it geometrically lives.
That would change everything.
It really would. Just something to think about the next time you spend 20 minutes organizing your desktop. Think about the exact mechanical process of what you just did to play this audio. You tapped a screen, and instantly, a piece of physical hardware thousands of miles away woke up and sent a file across the bottom of the ocean right to your device. Today, our mission is to understand the web's core architecture by analyzing a presentation deck called M0.5, the Internet in 8 minutes.
Right, because we live our entire lives on this infrastructure, but the actual mechanical reality of it remains totally out of sight for most of us.
Exactly. So let's look at the first slide here, which outlines the client. This is your browser, your phone, or the app you're using right now.
Yeah.
And think of the client as a customer at a restaurant, sitting there looking at a menu and placing an order.
Well, or even like an incredibly impatient logistics manager. I mean, it doesn't just calmly ask for a web page. It demands specific data packets, sets a really tight timeout window,
Right.
and just waits to quickly assemble whatever pieces come back first.
It wants it immediately.
Right. And that waiting period, which feels like a fraction of a second to you, kicks off a massive chain reaction.
Yeah.
Your client fires a request out into the physical world looking for a server.
Which brings us to the next slide, the server. And I feel like this completely shatters the whole illusion of the cloud. I mean, the internet isn't some ethereal mist floating above our heads.
No, not at all.
It is physical hardware. These servers live in massive temperature-controlled data centers out in the real world. They are essentially always on computers stacked with hard drives, built to answer those impatient logistics managers 24/7.
Yeah, the old joke definitely rings true here. The cloud is really just someone else's computer.
Right. Okay, so moving to the third slide. We get to the actual conversation, the requests and responses. My phone places the order by sending what the deck calls a JET request.
Which is quite literally a command asking for data.
Yeah, and when successful, the server replies with a 200 status code, meaning, okay, here is your data. But I have to push back on the hardware aspect for a second here. If a server is just a physical computer in a data center, how does it not instantly melt down when millions of clients send these GET requests at the exact same millisecond?
Well, that right there is the core tension of network engineering. engineering.
Really?
Yeah, and the server slide specifically notes they are built to respond and handle concurrent data flows. They don't crash because of load balancing. Imagine a massive toll plaza on a busy highway.
Okay.
Instead of all millions of cars trying to cram into one single lane, the server acts as an incredibly fast dispatcher. It instantly routes incoming traffic to hundreds of open lanes, queuing and resolving them in milliseconds so no single processor gets overwhelmed.
Wow, okay, that toll plaza analogy makes perfect sense. These are enterprise-grade machines engineered to just not buckle. But how do the requests even know which toll plaza to drive to?
Let's move to the final slide, the globe icon, detailing the trip.
Right, so this is where DNS comes in, the domain name system. Think of DNS as the internet's GPS. When you type in a web address, your browser doesn't actually know where that server lives.
It just has the name. Exactly. It asks the DNS, which translates that human-readable name into a specific IP address like the exact numerical coordinates of the server.
And once your client has those coordinates, your DET request physically travels.
Yes, we are talking about literal pulses of light shooting through fiber optic cables running across the ocean floor. And then the server's response travels all the way back to paint the page on your screen.
So synthesizing all this for our listeners, every single click you make, every time you tap a link, you are initiating a massive, instantaneous, global conversation.
It's a huge undertaking.
Pulses of light traveling across continents, routing through toll plazas, grabbing files from physical drives, and racing back to your hands.
And given the sheer complexity of this microscopic worldwide trip happening in the blink of an eye, it leaves you with an interesting puzzle.
What's that?
Well, the next time a web page fails to load and you're just staring at a blank screen, you have to ask yourself, where exactly did the conversation break down? Did your client's request get lost in the dark on its way under the ocean? Or is the server simply refusing to answer? Imagine writing a brilliantly crafted email, like poring over every single word, but the person receiving it only understands binary con.
Right, just ones and zeros.
Exactly. No matter how eloquent your words are, they mean absolutely nothing without a translator.
Yeah, that's completely true.
So today, we're doing a deep dive into the invisible translators inside your computer. You write human-readable source code, but your CPU only speaks machine code.
It's a massive mechanical gap, honestly.
Right, and we're looking at exactly how that bridge gets built.
Because the CPU hardware, it operates purely on electrical signals. It is completely blind to the syntax of a programming language.
It just sees voltage, basically.
Basically, yeah. So the system fundamentally requires a mechanism to ingest your text and, output executable bits.
Makes sense.
And what we are exploring today are the two dominant architectures used to actually achieve that translation.
Because the method you choose actually changes how you build software, right?
It completely changes your workflow, yes.
Okay, so let's start with the heavy lifter. If I write a program in a language like C or C++ way, how is the machine actually turning my text into those electrical signals?
So those languages use what is called a compiler. A compiler takes a very comprehensive approach.
Okay.
It scans your entire source code file from top to bottom all at once.
Just the whole thing.
The whole thing. It analyzes the logic, allocates the necessary memory space, and converts it entirely into machine code before a single instruction is ever executed.
Okay, so it creates like a standalone executable file.
Exactly.
So if writing code is like constructing a building, a compiler acts as the heavy machinery that, builds the entire structure all at once.
Every wall, every wire.
Right, every plumbing pipe, before anyone is even allowed to step inside.
Yes, that is a great analogy. And because that structure is already fully built and inspected, the moment you open the doors, it operates at lightning speed.
Because the heavy processing already happened.
Right. The heavy processing overhead happened during that initial build phase.
Oh, got it.
So when the user actually clicks the application, the CPU is just executing pre-optimized machine code.
Okay, I get why that's incredibly efficient for the end user. But thinking about the developer for a second.
Yeah.
If a compiler is doing all that heavy lifting up front, what happens if I just want to test a quick single line of math?
That is the catch.
Like, do I really have to rebuild the entire skyscraper just to see if the front door works?
Well, you don't, provided you are using the alternative method.
Which is?
An interpreter.
Okay, an interpreter.
Right. An interpreter skips that massive upfront build step entirely. The moment you want to run your program, it kicks in and translates your code one single line at a time.
Oh, just entirely on the fly? Entirely
on the fly. It reads line 1, translates it, executes it immediately, and then just moves to line 2.
Wait, hold on. That sounds a bit risky.
How so?
Well, if I'm building a massive program and I have a typo on like line 10,000, is it going to run perfectly for the first 9,999 lines and then just crash while a user is actively using it?
It will do exactly that, yes.
Oh, wow. That sounds terrible.
Yeah, because the interpreter is only looking at the instruction right in front of it. It is completely unaware of a syntax error further down the document.
So it hits that bad line, it just gives up.
It fails to translate it and halts the entire program instantly.
That sounds like a nightmare for catching bugs before releasing a product. But I assume the trade-off is the speed of development.
Exactly. You write a line, you run it, you instantly see what it does.
No waiting around.
Right. The friction of waiting for a long build process is completely removed. That rapid iteration is highly preferred in certain environments, especially for prototyping new ideas.
Let's ground this in something you might actually use today. Like Python is massively popular right now.
Oh, absolutely.
Especially for people just getting into coding.
Yeah.
So where does Python fall?
So Python is structurally an interpreted language. You write the code and run it immediately without a manual compilation step.
Right, you just hit run.
Exactly. But to address the performance issues of reading raw English text line by line, Python does something quite clever under the hood.
Oh, really? What's that?
It utilizes a hidden step where it actually compiles your text into bytecode.
Okay, break that down for me. What exactly is bytecode?
Think of bytecode as like an intermediate language. It is not plain English, but it's not machine-level binary either.
Like a middleman.
Yeah, exactly. When you hit run, Python does a very quick, rough translation of your script into this stripped-down, simplified format.
Gotcha.
This bytecode is much easier and faster for the interpreter to read line by line than plain text.
Oh, that makes perfect sense.
Yeah, which optimizes the execution speed without sacrificing that instant startup time.
It's doing a quick shorthand translation first so the actual line-by-line reading goes smoother.
Exactly.
And that immediate feedback loop, combined with the hidden speed optimization, really explains why Python is uniquely suited for beginners trying to learn quickly.
Oh, for sure. It provides a highly interactive environment.
You get that instant validation.
Right. The system feels alive and responsive, which really builds confidence when you are learning complex logic.
So here's a thought to leave you with as you think about how software gets built.
Okay.
If interpreters stop at the very first error they hit, essentially forcing you to fix things incrementally on the fly,
Right.
and compilers force you to translate everything perfectly up front before you can even see if it works.
Yeah.
How might choosing between them completely change the psychological way you approach problem solving and writing your code?